This video is on how technological innovation happens. A lot of this will be incorporated into a video on communism and central planning I am hoping to make eventually. The major way innovation occurs is trial and error processes in the actual production facilities through experimentation and adjustments in the procedures and equipment. Formal industrial research does not eliminate the role or need for such processes. Processes and technologies developed in research labs very often have to be altered to work in the real world and in actual production facilities. There could be a variety of reasons for this. The processes and equipment could work differently on the scales necessary for industrial production. The environmental conditions at the facilities might be different than in the controlled lab settings and affect the processes. Or long-term and continuous production could cause wear and tear that affect the equipment, and new ways must be found to deal with it. What works and what does not, and what works better than what else, has to be learned through actual experience. Offline R&D cannot replace the need for testing in actual practice, and competition between alternative approaches. The people who work with the equipment every day will have a superior vantage point for understanding how it works better than anyone, especially if they are technicians that already have all the required scientific background knowledge, and so have insight into how to improve things that no one else has, or can have, including the research scientists and engineers that originated the processes or equipment in the first place. Often, the people who work in the production facilities spontaneously stumble on ways to improve the production process, and that automatically creates innovation. Often, more formal lab research works in similar ways. As an example, when researching how to make a tungsten light bulb, William Coolidge found that the work had to be closely correlated with controlled decreases in temperature. He compressed powdered tungsten into steel molds to form ingots. He first baked them and then tried hammering them. He found that in hammering ingots, the first blow reduced temperatures, which interfered with the precise temperature controls needed to process the material. Coolidge then acquired swagging machines and redesigned them to work at precise temperatures, which will require new inputs. He then used smaller swagging machines with special compressing rollers. GE researchers then developed new types of furnaces to prevent tungsten coming into contact with impurities while maintaining precise temperatures in spite of constant movement of the machinery, which would require inputs not predicted when the research began. The lab research had parallels with the evolutionary processes of trial and error in production facilities. The research process involved playing around with the materials and responding to problems with the process immediately as they arose. Completing one step in the research process left and revealed new unforeseen issues that had to be resolved before the process could work. Every step in the research process presented new problems, creating spontaneous, unpredictable demands for new materials to meet the very different solutions for each problem. Even in the case of formal research by a laboratory scientist, the needs of the process cannot be predicted from the beginning, and suddenly require different kinds of inputs for each step. Such an undertaking can only happen if the former facility has control over its own material balances and inputs, and has the ability to suddenly procure varying inputs without causing significant disruption to the material balance of the rest of the economy. Semiconductors and microchips are perhaps the most important components of today's modern economy. They are required in practically all modern production processes, and a modern economy simply cannot be run without them. The manufacture of semiconductors is an extremely complicated and difficult process. It requires more than 100 different steps of coating, baking, etching, etc. Many of these steps are not well understood and impose demanding requirements for a particle-free manufacturing environment. New product innovation requires innovation in the processes. A lack of understanding for new equipment's operating characteristics often has to be introduced with a new recipe that is also not well understood to manufacture a new product. The complexity of the manufacturing process also means isolating and identifying causes of yield failures, which requires considerable time and effort. There is a need for new R&D for each new generation of microchips. Such a complicated and delicate process means that production and output is sensitive to any environmental differences or slight differences in the locally available materials, such as the local area having a different background electromagnetic field that interferes with the process, or different trace pollutants in the atmosphere that interfere with a step that can't take place in a clean room, or maybe the existing clean room equipment can't remove as well. The locally available material could have different trace impurities that cause it to react differently at a key step. Any one of these hundreds of production steps can be affected by these environmental and material factors and render the final product unusable. Simply copying the blueprints will not work. New independent innovation is required to fine-tune the process to work under the different local conditions. Trial and error evolutionary processes remain an essential component for innovation, and industrial research cannot eliminate their necessity. Furthermore, formal laboratory research occasionally veers off in unpredictable directions that parallel or approaches those on-site trial and error processes. Innovation in production can only take place in an environment where firms can have control over their own material balance and inputs, and the economy's organization is flexible enough to handle sudden and unexpected procurements of inputs. To allow for innovation, an economy needs to have the ability to have resources suddenly redirected and simultaneously still maintain a functional material balance. Eventually, technology gets too complex for simple blueprint copying and requires additional new innovation to work under the different local conditions. Without technological innovation, economic growth cannot ultimately occur. So these are the references. They'll also be in the description. And that's it for the video. Please like the video, leave your thoughts in the comments, subscribe to my channel, hit the notification bell, and share this video with anyone who might be interested in it.